Okay, this is the last topic for the chapter. Okay, so we're going to have a test early next week. These are the difficult Lewis structures that you've never learned how to do. And we've kind of been okay with learning the Vesper theory and learning all the other stuff we've done, just doing relatively simple ones. But every now and then we ran into problems, like with carbon dioxide, right? And with the other place we saw double or triple bonds, the nitrogen molecule or the oxygen molecule. When I'm done with today and tomorrow, you will know how to do those from scratch. It won't be like you'll be just guessing and trying to fit a puzzle piece together for your octet rule. You're actually going to have a system, and that's what I need to teach you. I never used to do this because it is basically difficult. It takes days and days to really get it down, and I didn't like to waste the amount of time that it required to do that. But I realize now I have to have it. There wasn't much on the last AP exam, but there could be on the next one. It all depends, and you just never know. So I have to teach you all this stuff about how to do Lewis structures, the really difficult ones, which I'm going to start with easy ones to use. Now, I have, because it would take literally, it's going to be 2 times the, there'll be 16 slides coming up here. I don't want to have to write all this crap. So I've got most of it filled in for you on here. And then we're going to do the examples together. So you don't have to be writing all these notes down and wasting our time. You just can follow along with me, all right? So let's follow along and show you the actual system. I'm going to take it step by step early on. Believe me, it doesn't take this long. It's going to take me, 3 boards to show you how to do a problem that takes probably about 1 minute or 2 minutes to do. So it doesn't really take this long normally, but I want to show you so you all understand. All right, you're going to use this needed, available, shared method, okay? And basically what you do is you figure out, first of all, how many electrons are needed. If everybody gets happy, if everybody gets their octet, how many electrons would be needed? So if I'm talking about a very simple compound, like we were doing oxygen the other day, all right, and it turns out to not be really simple. All right, oxygen, 2 oxygen atoms, the O2 molecule, has if each one of them were to be happy, it would be nice if it could be like this, wouldn't it? Right? It'd be nice if everybody had 8. All right, but unfortunately, that's not what happens, and we'll see why in the end. But that's what you write first. The first thing is just determining how many everybody would be happy with. And everybody would be happy with usually 8. But there are some exceptions. Oops. There are some exceptions. Most atoms want 8, but hydrogen only wants 2, and beryllium only wants 2, and boron wants 6. I kind of have that a little backwards, but we don't use beryllium. I'm not going to even use beryllium, I don't think, in very many examples. But hydrogen, obviously, we knew that. Hydrogen is only 1 away from helium, and really, we call it the octet rule, but really it should be the noble gas rule, because everybody doesn't want to have an octet. Everybody wants to be like the nearest noble gas. We know that from last year. Nearest noble gas for hydrogen is helium. That's why he wants 2. That will give him a full shell, the only shell he has, a full energy level. Boron's weird. He wants 6, all right? And there are other exceptions, but these are the only ones I'm going to teach you, okay? Let's talk about, let's do some examples with this, okay? For water. Again, you don't have to write this. It's already written down for you. There are 2 H's. H is happy with 2, so 2 times 2 is 4. There's 1 O. O is happy with 8. 1 O, there's 1 oxygen in here. He'd need 8 electrons. Total amount needed, 12, right? What if I were to do CCl4 for next, okay? Well, carbon by himself, he'd like 8 total. By the way, notice what I'm saying. I'm saying total amount needed, total. Actually, a lot of times when I asked that question in Chem 1, I said, how many does carbon need? How many does he want? You guys would have said what? No, carbon. Look what group he's in. 4. He'd want 4, right? And fluorine would want 1. That's not what I'm asking here. Now it's a different system. What I'm asking you here is carbon totally would be happy with 8 around him. So would chlorine. But there are 4 chlorines, so 4 times 8 is 32. Total number of electrons we're going to need to throw in to make these guys happy, 40. And there's one other guy here. I'm going to make it a polyatomic ion. That's going to start with the hard ones, but that's not the end of the hard ones. Polyatomic ions, they've got a charge. That means something. It's going to mean something in a minute. But right now, all we care about is I have 4 H's and 1 N. Tell me, without me doing it, me blocking it. I can't really block it. How many total am I going to need? Can you do that in your head? Each hydrogen wants 2. The 1 nitrogen wants 8, right? 4 times 2 is 8. 8 and 8 is, y'all figure 16? That's how many are needed. Got it? All right. This is easy. They're all right there. All right. Next, available. This is the next part of this. I want to see how many electrons do you actually have, does each of these elements actually have? In the case of valence electrons we're talking about. In the case of the halogens, fluorine, chlorine, bromine, ion, we use them a lot. They have 7 because they're in group 7, right? Carbon's got 4. All right, so we're also going to have to do this for polyatomic ions. And yes, you are going to get polyatomic ions on the test and especially at the AP. You have to add or subtract electrons for a polyatomic ion. Now, it makes sense that you would add for negative polyatomic ions. Let me show you why. Say I've got the sulfate ion, for example, which has a -2 charge, which, by the way, most of the time you'll see it written 2 negative. I always write -2. Just an old habit, but it should be 2 negative, same thing. What you're saying here is, I got 2 extra negative charges. Where do you think they came from? 2 extra electrons. Aren't electrons negatively charged, right? So you're going to have to add, if you've got a polyatomic ion, besides what you have here and here, you add 2 more on for the sulfate ion. Okay, and we'll see that. If we have a positive guy, you're going to subtract. It means he's missing an electron. So for water, how many are available for this guy to be able to throw around? Well, each hydrogen only has 1. I've got 2 hydrogens in water, so 2 times 1 is 2. There's only 1 oxygen. How many, before this comes up, I mean, without looking down at your paper, how many are going to be available for oxygen? 6, right. And then total number available, 8. 6 and 2 is 8. Just add them together. Same thing for carbon and chlorine. I've got 4 chlorines and 1 carbon. Carbon's got 4 available because he's in group 4. Chlorine's got 7 available, and there are 4 of them. That's 28. Total amount available is 32. And finally, for the ammonium ion, I've got 1 nitrogen with 5. He's in group 5. I've got 4 hydrogens. Each one has 1. That's going to give you 4. Now, here's the crazy part. Okay, what you have to do extra on top of that. Because he's a +1, right? What does that tell you? He's missing an electron. So you got to subtract 1 electron, right? And therefore, you have a total of 8 available. Got it? All right, again, you are not doing this in every problem. The problem itself is going to be really quick when I get to the example. I'm just showing you where all this, what I'm going to write when the problem gets there is going to be this, N-A-S. I'm showing you where the N and the A and the S are coming from with these slides. Not trying to get you to say you have to do all this crap every time. You don't. All right, let's finish it. What about sharing? Well, here's the deal. God bless you. The deal is, God bless you. The deal is, once you know how many available I have and how many sharing, if those 2 numbers are exactly the same, you know, well, it would be kind of weird because you wouldn't have a bond. But chances are they're not going to be exactly the same. So what do? You're going to have to subtract. You're going to have to subtract the 2 to find out how many bonds. If they were exactly the same, obviously they both already have octets. They wouldn't want a bond. All right. So it's not going to be exactly the same. You're going to have subtract. So let's do those subtractions. For water, it's 12 minus 8, 4. So this is important. Watch this. 4 shared electrons is how many bonds? 2. Because remember what a bond is. If I could have written, and we've done this before, I could have written like methane, for example, like this, and that's correct. Or I could write them like this. Right? Because a bond, a line, a dash, represents a pair of electrons. So if I've got 4 electrons, that means I must have 2 bonds. That's the equivalent of 4 electrons, okay? All right, rest of them, do quickly. Hit that already. 40 minus 32, we did the 40 for the first slide, 32 from the last slide. 8, that means you have 4 bonds. And 16 minus 8, you have 8, that's 4 bonds as well. No problem so far. Okay, let's do these quickly. Now you have room right underneath this, I believe. Is that correct? Or no? We didn't get to this part here. Skeleton structure. All right, so it's time to start our problem. Now we're going to do these after I give you a little bit of notes in the space provided. I want you to leave the big space where it says example. Leave that free for tomorrow when we do a few more examples for fun. But for right now, I'm just doing. Yeah, they won't be fun. But leave that space free. So what I'm saying is you're going to want to put your answers right underneath here and then leave under examples some free space. All right. So in the skeletal structure, what you have to do is, most of the time it's pretty easy. If I've got a very small compound with just 2 elements in it, there's really nothing to draw. But if I've got 3 or 4 or 5 elements, I may have to put a guy in the center. Who do you put in the center? Well, you generally want to put the least electronegative element in the center. And you'll get used to seeing certain guys that go in the center, like carbon. He's almost always in the center. All right. Then you're going to use the bonds, your dashes, to represent how many bonds. You figured out that from the needed available shared, and connect the guys together somehow. The first 3 examples I did here, they all connect nicely, and everything works out beautifully. And you could have done these your old-fashioned way of just trying to fit them in and make an octet. But you're going to find right after I do these, the hard ones don't do that. All right, so let's do these. Okay, I have enough room, but I don't really want to work way down here below. Let's do these 3, and you're going to do them too. Now, I'm going to go back here. On this board is where we're going to do it. Leave this one for water, and then CCl4, and then ammonia, like right across your paper in that space above examples. Okay, let's do water first. All you would write for water would be needed, available, and shared. Okay? And again, we could have done this guy without this system. I'm showing you the system using easy ones first. How many are needed? Watch me up here. Just watch. Well, oxygen wants 8, and hydrogen wants 2 apiece, right? Or 2 hydrogens. So 8, and then 2 times 2 is 4. 8 and 4 is what? 12. How many are actually available from this guy? Well, what group number is oxygen in? 6. So he's got 6 valence electrons. Hydrogen only has 1, but there are 2 of them. So 2 and 6 is 8. So we all agree there's going to be 4 shared electrons there. See how much Hey, I just spent 3 boards doing that nonsense. And that's how much actual work is involved. Not much. All right, and this tells me, this S equal to 4, the shared 4, tells me that I have 2 bonds. You just divide it in half, right? Because for every 2 electrons, you've got 1 bond. Now, I draw my oxygen and my hydrogens, and I have to connect them somehow with 2 bonds. Well, how hard is that? I mean, it's not very difficult. And by the way, we all know it's going to look like this when we do the Vesper theory to it. But if you had drawn it like just right across, H-O-H, I wouldn't take off for that, because technically I'm just asking you to do the Lewis structure. I'm not asking you to tell me what the shape is. I could ask that later, and then we could ask that question, which I've been doing for the last couple of days. So there it is. I took care of my 2 bonds. I always take care of the bonds first. And then you have how many leftover electrons? Well, 4 of the available have been used for bonds. We have 8 total available. I've used 4. So how many are left? 4. 2 pair, right? But 4 electrons. Where are they going to go? Well, are they going to go around H? That's not going to give him an octet. He's already happy. H is happy. But oxygen's not. So those extra 2 pairs of electrons, the extra 4 electrons, are going to go around oxygen. This is exactly what you would have drawn had you drawn this yesterday or the day before or last year in Chem 1. But now you have a reason for having drawn it this way. All right, the next one over, I'm not going to have room to do the third one. I'll do the second one here. This was going to be, so don't make this so huge. This was going to be the CCl4, right? By the way, you're done with that. That guy is done. Now, I can, if I wanted to right now, apply the Vesper theory to this guy. How many things are bound around an essential atom? 4. 4 electron regions. 1, 2, 3, 4. Only 2 of which are actual bonds, actual atoms, so that means he's bent, and that's 109.5 around that. Okay, needed available share. Okay, my needed? How many are needed? Well, I have, really, this is, you start getting good at math with 8s. There's a reason we don't use, the decimal system is based on 10s, right? It's a lot easier to do the math on 10s. But math on 8, you get used to it. I've got 5 total elements here, right? 4 chlorines and 1 carbon, all of which want 8, correct? What's 8 times 5? 40. So you just get good at using math with 8s. How many are actually available? That's not so easy. It's always a different number. Chlorine has 7. 7 times 4 is 28, right? 28, and how many carbon have available? 4. 28, 4 is 32. Subtract those 2, you get 8. Is that correct? 8 shared electrons means how many bonds? 4 bonds. You see why? It's just half. A shared pair of electrons is a bond. They're the same thing. Good. All right, now I write out my CCl4. I want to put my least electronegative element of the 2. Chlorine is more electronegative than carbon, and you should know that. As we go up and to the right of the periodic table, right, you know that's what happens. You get more stronger electronegativities. Okay, so I put my C in the middle, and I put my Cl's with 4 bonds around it, connecting those guys. And once again, things are just going to work out beautifully, because the next step is to try to give everybody an octet, right? I'm going to try to give everybody an octet. Okay, well, chlorine needs 2, 4, 6. And so does every other chlorine. And now let's try adding them and see how many we have. Before I do it, when I add all these guys up, what should it come out to be? What number? 32. It has to come out to be the available number. I can't have created or destroyed electrons, correct? So, let's do it. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. That is 2 there. 32 is what I came up with. 32 is the number I had available. That's perfect. Okay? That's what we want to happen. Great? Sometimes it won't. I'll talk about that next period, not right now. All right, last one then. This one's the only one that's a little bit different. Is the ammonium one. Okay? Needed, available, shared. You want to fit this one over to the right side? How many are needed for nitrogen and a hydrogen all put together? What do you think? Well, nitrogen wants how many? Total of 8. Again, I know I'm seeing people looking up there and thinking, well, he wants 3. No, I'm talking about total. Total. 8. Each hydrogen wants 2 total. 4 times 2 is 8. 8 and 8 is? Y'all get 16. See what I'm doing there? Available. How many are actually available to these guys? Well, each hydrogen has only 1. And there are 4 of them. 4 times 1 is 4. Nitrogen? What about him? What group is he in? He has 5. 5 and 4 is 9, but there's a problem. It's not really 9, is it? Because of this up here. What does that tell you about this ion? It's missing an electron. It should be there, right? So what do? So I get 8. So 8 from 16 is 8. Got it? All right. Now, I put my nitrogen in the middle because I have to. I mean, there's H's around them. And I make my bonds. Those are my bonds, right? Let's add up our electrons. Do we come out with the number we should come out with? 2, 4, 6, 8 is what are in here. 8 are what were available. We're good. Everybody's good. All right, well, you say to yourself, geez, this is silly. And you're absolutely right. You can probably see how I could have taught you how to do these easy ones, and I did teach you how to do these easy ones in Chem 1 without this method. Just with the basic understanding of the periodic table, the group numbers, and the octet rule, you would be able to do this. Great. Here's the problem. Watch what happens now when we get to this next couple of examples here. Okay? All right, you have all those papers? What's the next paper say? Yeah, let's get to those double and triple bonds. Watch this. This will help us do the guys that have been giving us trouble for the last couple of days. Double and triple bond guys. Sometimes when you do this, turns out you get more bonds than you have atoms. What happens if my needed, available, shared says I should have 3 bonds, but I only have 2 atoms? What do? Well, that's what I'm going to show you. Okay? Let's try carbon dioxide. Let's try it. He's one we've already seen before, but now I'm going to show you something interesting about it. Watch. And this one, we're going to end up using, well, that's not true. I'm going to do that in the second example. Just this one, it's okay. Needed, available, shared. Do that yourself, right now. Do the needed, available, shared yourself right now. We've just done 3 very slow examples. You should be able to do this. Did you get that for your needed? Did you get that for your available?
No.
How do we get available?
Doesn't oxygen need to come out?
Available, not needed. Available. How many electrons are in oxygen? What group number is he in? 6. How many oxygens are there? 2 times 6 is?
Oh. Yeah. Never mind.
Other people, what was your mistake?
Yeah, same
thing? Okay.
I was thinking like.
Somebody, a lot of people are again available. They're thinking, oh, for whatever reason, I need 2 for oxygen. I need 4 for carbon. No, it's how many they have available. Okay. See, that's why it's 16. Got it? All right. Shared. How many? 8. So how many bonds are going to be there? Don't. Just let me keep watching. This is not the last example. Here's the test. I'm going to be teaching for the next 2 periods. You will get it. You will get it. Trust me. All right. So we have 8. So that means how many bonds? 4 bonds. Okay. Now that's a problem. That's a very big problem because carbon, being less electronegative, I'll put them in the middle, and I've got my O's on either side. My work is saying I need 4 bonds, but I've only got 2 places to put them. So what do? Yeah. 1, 2, 3, 4. This explains why we use a double bond. In the past, I've kind of had to just say, well, I went through a whole big rigmarole of why you're violating the octet rule, this, that, or the other thing, but you're just kind of guessing. But now you're not guessing. You have to have, when you get done with this, you got to put 4 dashes somewhere. You'll know exactly 4. There can't be 3, it can't be 2, 4. And you will put them like that, right? Now, I'm not done yet. Hold on a second. Is carbon happy with his octet? Is he?
Yeah.
2, 4, 6, 8. Absolutely, he's happy. But is oxygen? No. So I'll make him happy with an octet. Oh, and by the way, really you should put him, we all know this from the Vesper theory, you kind of want to put him like that, wouldn't you? They'd want to get as far away as they could, wouldn't they? See what I'm saying?
Sure.
But if you did this, I'm not going to take off. I'm not going to care a whole lot. On an AP exam, you really should do it like this. Okay? Is everybody happy now? Well, let's see. Is oxygen happy? He's got 2, 4, 6, 8. Oxygen's happy. This oxygen's happy. 2, 4, 6, 8. And carbon's happy with 2, 4, 6, 8. So everybody's happy. And last thing to check. Does my available equal these over here? Do it quick. 2, 4, 6, 8, 10, 12, 14, 16. Perfect. That's why carbon dioxide looks like that. Now I'm about to blow your mind. Carbon dioxide does not really look like that. There are other possibilities. Can anyone think of a creative way I might have connected these guys using 4 bonds? And we'll say, okay, well, maybe I'll screw something else up. Well, let's see. I want to make this guy happy. What does he need over here? 2. Carbon's happy, right? 2, 4, 6, 8. By the way, don't draw this guy. 2, 4, 6, 8. Did I violate any rules? 2, 4, 6, 8, 10, 12, 14, 16. Yep. That works. Don't write it. I'm going to explain why it works and how it works and why it's not your best answer, but it's still an answer. Absolutely it's an answer. In a little bit when we talk about resonance structures. And I could have also put that triple bond over here. So, yeah, told you I'm going to blow your mind. These are called resonance structures. When more than one possible answer can work, you actually can get more than one answer, and you end up getting like a mesh of all these guys, like a hybrid of these almost. It's called a delocalization of the electrons over the sharing of these guys. And I'll explain why how you do these resonance structures in a little bit. But for now, let's just do another one of these guys. Do this one entirely on your own. HCN. Needed, available, and shared is not a problem. Everybody can do that for this guy. Once again, I'm going to write it up here higher so you can see it better, but you'll be writing yours right underneath here. Everybody can do needed, available, and shared in this. I know you can, and if you're saying I can't do it, I don't care if you get it wrong. I still want an answer. Everybody should be trying this. Austin, what do you think? How many are needed?
18.
He says 18. 8, and 8 is what? 16, and then one more H needs 2. And again, needed means the total. It's almost always going to be 8. The exceptions being hydrogen, boron, and beryllium. And they're the only ones I'm ever going to give you. So 8, 8, 16, and 2 more is 18. Very good. That's how much you need to be happy. How many are available? That's easy too. We now are got it out of our heads. Because all last year I was talking about, oh, he wants this, he wants that. How many are available? What group is he in? N is in group 5. Carbon's in group 4. 5 and 4 is 9, and 1, 10. Agreed? That means 8 are shared or 4 bonds. That's what you all should have at this point after having done this many. All right. Now, the C is going to go in the middle, and the H and N around him. Okay? I need to put 4 bonds. You might think to yourself, well, is it going to be like the last one where I have more than one choice? What do you think? No. What happens if I try to put a triple bond over here? Yeah, hydrogen doesn't want it. He says, thank you, no thanks. I only want 2 electrons, and don't give me any more. There, I'm happy. Now, I can fit that guy over here, can I? And I do. Now, am I done? No. I have to make everybody happy. Is hydrogen now happy? Yes. Is carbon happy? Yes. Is nitrogen happy? No. And I'll put those electrons as far away, Vesper theory, as they can go. And that is HCN. How about that? Okay. Well, let's start talking about the resonance structures now. Because as you've seen, I can, in some cases, have more than one possible answer. More than one way to satisfy the octet rule and make everybody happy. And when that happens, I've got to write them all down. So let's do some examples here. You ready? Let's start with NO2 with a -1. I'll do this one with you, and we'll see what happens. Needed, available, shared. If you still haven't figured this out, let's see if we can do it. 2 O's, 1 N, 3 total, times 8. 8 times 3, 24, right? There we go with that for needed. Available, 2 O's, each one has 6. 2 times 6 is 12. So 12 and 5 from nitrogen, he's in group 5, is 17. But don't keep it at 17. What do I then have to do with that guy? I have to add 1 more electron because of that -1 charge. So it's really 18. All right, 24 and 18. 24 and 18, difference? 6. Which means I'm going to have to put 3 bonds in between these guys, even though there are really only room for 2. So what will I do? N clearly has to be the central one in this case, and O and O. I don't care where you write them. It's not going to matter. Oh, no! Okay. Oh, no. All right, that's it. You're done. No, that's not right. Hold on. Okay. Now, in this case, I've got to put 3 bonds, and you might say to yourself, well, let's see. You guys put them where you want to. Go ahead. And then I'll draw them up here, and I'll get the obvious question after this. How many of you drew them with the 2 bonds on the right? About half of you. And the other ones drew it with the 2 bonds on the left, right? Yeah. And that's because both of them can happen. Let's finish them up. Let's finish this one up first, though. The guy that has 2 bonds here, and this O right here, how many more electrons am I going to put around him? And where should I put them? 2 more pair, like that. Y'all agree? To make him happy. How many have to go around this O? And am I done? No. Is nitrogen happy in the middle? What does he need? Okay. Did I violate any rules? Let's double check. 2, 4, 6, 8, 10, 12, 14, 16, 18. Yeah. Now, the other side of that coin would be if I did this. And you need to do this. Whether you have room, you can put yours over to this side too. That's fine too. All right. Here's why I'm doing that. Some of you are saying, well, does it really matter? I mean, aren't they exactly the same thing? Here's why it matters. And you're going to find this when I give it back. In the next period, I'm going to give back to you something that you did already and have a wrong answer for that I did not take off points because you didn't notice at the time. You don't really have one double bonded oxygen and one single bonded oxygen. What you really have are 2 NO bonds that are kind of like a hybrid between, or a resonance structure between the two. Where the electrons, you don't, in other words, the properties of this bond are really no different than the properties of that bond. They're both kind of in between a double and a single bond. All right, they're sharing these electrons over the course of these two. Like they're not flipping back and forth. They're kind of like creating this hybrid almost. All right, but you would have to draw both of those. Okay, let's draw another one. CO2. I'll have to, I'm actually going to leave this guy up here. No, I'm not. I'm going to erase this guy. Now, we've already done CO2, so I'm not going to waste our time doing the available share, right? Don't we all agree that this is what carbon dioxide looks like? Now, let me do that better. Oh, my God. We all agree that we did that just a minute ago, correct? That's the only one you wrote down. Now, Austin was nice enough to give us a different perspective on that. He said, you could have, why couldn't we do this? Or this. And he was right. We could. Finish up the electrons in all of these. Right? Correct? And vice versa over here. Oops. Ignore that thing there. Ignore that little blob up above. I can erase it if you want. Okay. These are the 3 resonance structures for carbon dioxide. They are not all created equal. Which one do you think is the best one? What do you think? The first one is the best one, but not for what reason you think. It has to do with something called formal charges, which I'm not going to do in this period. I'm going to let you guys work on some of these, practice some of these. I might get to it by the end of the next period, because just to make sure I cover it during this day. But I'm going to let you work on some problems in between. Now, that is the best one. You might think that's the best one because it's the most even, it's the most symmetrical, whereas this guy kind of looks a little weird. All right? But that's not really the only reason. And I'm going to try to tell you why when we get some other examples here. Watch. I have 2 more to do. We only have about 10 minutes left in the class, so let's do this one here. This one I want to have up here, God bless you. I want to have this guy up here for a reason while I leave this one up here, as you'll see. Let's do the needed, available, and shared on here. I'm going to do it up above, but of course you're just working below. Right? 3 atoms, all want an octet. 8 times 3 is 24. You get good at math with 8s after this for a while. Available, not so easy. 6 and 4 is 10, and 5 more is 15. But you got 1 negative 1 charge here. So what does that mean? Yeah, so it's actually going to be 15 plus 1, or 16. Got it? Shared? 8. Which means 4 bonds. 4 bonds for CNO. This is a beauty. I love this one. Okay? And I love comparing this one to the one above. Write your 3 possible answers there. Write your 3 possible answers there. By now, I'm hoping you should be able to at least give me 3 decent answers. Who's got to go in the middle, you think? C, least electronegative one of the 3 here. You all agree I could do this, right? I need 4 bonds. Can't I do that? What else could I possibly do? What's that? Well, not if I keep 2 bonds. That is exactly the same thing. No. Over here, what could I do over here that would be different? 3 here, 1 there, and then 1 and 3 there. Is everybody okay with that? Kind of like I did up here, right? Let's finish them up and make sure everything works out okay. Two, 4, 6, 8, 10, 12, 14, 16. 16, beautiful. How many remaining on this oxygen over here? Just 2 electrons. That's it. 1 spot there, 2 electrons. Anything on the carbon need it? Nope. But this nitrogen needs a whole bunch of crap. Is that right? 2, 4, 6, 8, 10, 12, 14, 16. Yep, that's right. And finally, two, 4, 6, 8, 10, 12, 14, 16. Got it? Here's the crazy part. Which one do you think's the most stable, happiest one of these guys? Well, it's going to be this guy again, right? Nope. Remember I told you a minute ago. It's not just because that guy looks the best, because he's the most symmetrical. Nope. It has to do with something else called the formal charge. You're going to have to wait, those of you at home, you're going to have to wait, for the next installment. This is like one of those cliffhangers, at the end of the season. We'll be back next year. You don't know if the guy's dead or alive. Speaking of which, I think Longmire starts. Yeah, tomorrow's experience. Longmire starts the new season. You guys don't watch that show. It's on Netflix now, though. They picked it up. Anyway, it looks with a cliffhanger. You don't know who's dead. Somebody's dead, but you don't know who. So, anyway. All right. I'll get to that. I'll get to those guys in a second. But this last one is going to see if you can do this one on your own. Totally. And this is the last one we're doing. Hopefully you're getting good enough at these to be able to get these right. Writing the possible answers here. How many resonance structures can you guys come up with?
Hold on. You gave us like
I just did it.
30 seconds.
Oh, you're as smart as me. I've just been doing this too long. Let's just make sure everybody has a needed available shared, right? Because if you have that wrong, you're going to have some problems, right? You're needed, I have, so I don't have to think again. Was it 32, right? And then 22 plus 2, right? So it's 24. So that means what? 8 or 4 bonds. Right? Why is it 22 plus 2? 22. Well, you get the 22 from 6 of these, and 4 of those is, well, 3 times 6 times 3 is what? 18. 18 and 4 is 22. 22, and then the negative 2 is 2 more electrons. That's 24. Okay, so everybody's good with that? Now, I got to put 4 bonds around CO3. Obviously, C has to be in the middle, right? And I have to have the O's around, right? Look, this is really not that hard. How many resonance structures will there be? Why? How many? 3. Right? Or, what about this guy? Oh, I made a line on the line. I can do this, right? And what's my other last possibility? Oh, and by the way, if it is a polyatomic ion, I am remiss, and I'm glad I remember this while the cameras are still rolling. If you have a polyatomic ion like you had here, and like you have here, you have to put the whole thing in brackets and the charge above him, which is what? In this case, 1 minus. In this case, a 2 minus. What? What do you mean? What?
Wait, what did you just say?
Anywhere where there's a polyatomic ion, like these, you simply put a bracket around the whole thing when you're all done. Okay? All right, now, am I done with all these? Are these all written correctly? No, you got to have the electron dots correct. 1, 2. Okay? And you have to do that with all of these. But we're running out of time. The bell's, I want you to take a break. But, you fill in electron dots around all these correctly. When I come back and start talking about formal charges, I want to also mention something to you about one of your examples in your problem. But that's it for this. Okay, take a quick break, and we'll be back.